So how do we solve the Navier-Stokes? So right now I'm giving you an extremely broad overview in this slide of how we typically solve it in the pressure-based method. So basic idea is we start with a guess of U, V, and P, our three unknowns. Okay, this is for 2D. I'm going to call that iteration k equal to 0. Okay, and then since I have my U, V, and P, I can calculate my link coefficients and sources. If you look at these expressions, if I know my U, V, P, I can calculate all these quantities, okay, including the source. Everything I can calculate. So I can calculate all those link coefficients, okay, and my source terms. So I'm basically calculating these guys, for example, okay, and that guy. My unknowns are still this advected velocity component, even though I've guessed my velocity component already. Okay, this is where the linearization of the equation has come into play. The link coefficients are calculated using a guess, but then we are solving the linearized form of the equation to predict a new velocity field, which we will again use to recalculate the link coefficients later on. Okay, so that's the idea. So we start with the guess, calculate link coefficients, solve your X momentum equation. This is where you're going to use inner iterations or sweeps. So for example, if you're using ADI, maybe you will use 20 sweeps of ADI, okay, or whatever the number may be. Or you may say, I want to solve it up to a certain level of tolerance, okay, whichever way. But those are what's called inner iterations. This is where all the stuff that you've learned in 6507 goes in. You're solving a single PDE now. You have the linear set of algebraic equations and you're just solving. Okay, it's like black box. Same thing you do with the Y momentum equation. Now notice that when I solve the X momentum equation, I'm automatically updating my U velocity, right? I have a new U velocity, but I'm not using that U velocity to recalculate my links. I'm using these same old links to calculate my Y momentum. Okay? Just because my velocity has changed, I'm not going to use it right away. This is important to understand because I sometimes see students that, oh, they've solved the X momentum and they're recalculating the links. Okay, and if you do that, later on you will see when we go through all the derivation, if you do that, you are actually violating the mathematics. Okay, because the whole formulation is based on the assumption that the links are frozen right here. You're not changing it. Okay. And then you solve continuity. Now, we haven't talked about this. Obviously, we still have this issue of, okay, how does the solution of the continuity give us pressure? We haven't talked about this, but conceptually, let's say we solve continuity after this. Okay, and again, this will require some sort of inner iterations, and that will give us an updated pressure. Okay, and then you check to see, have all three equations converged simultaneously? Okay, suppose this one converges and this one doesn't converge, then that means your overall solution hasn't conserved the two momentum equations and the mass conservation equation simultaneously. The three conservation equations need to be satisfied simultaneously. Just conserving one of them is not good enough. Okay, so that's what we mean by converged. If no, then you go back and redo everything. So conceptually, this is pretty straightforward, right? I mean, yeah, we have three PDEs, but basically we are solving a linearized form of each PDE one at a time, and then we are putting it in within a big loop, and this loop is often known as an outer iteration. So we have inner iteration versus outer iteration. Okay, and outer iteration simply means my k gets advanced by 1. That k is the outer iteration index. Now here you may have any number of sweeps. You can use a different counter for that. Okay. Everybody with me so far? So this is conceptually how a pressure-based solver, a segregated pressure-based solver would typically work. But there are many, many issues that we need to deal with, one of them being how does the continuity equation give us the solution for pressure? Okay, and this is where this algorithm, as you know, this is an acronym, the simple algorithm came into play. Okay, so simple stands for semi-implicit method for pressure-linked equations. Okay, couple of key points to note here is that it is an implicit, or at least a semi-implicit method. It is not an explicit method like the one that Harlow used. Okay. First ever implicit algorithm for solving the Navier-Stokes equation, developed by Brian Spalding and Suhas Patankar at Imperial College London in 1970. So this was basically Patankar's dissertation, PhD dissertation. Okay, if you go and read his thesis, you will find that he solved this driven cavity problem and backward-facing step problem, which are the two problems you are going to solve. On the driven cavity problem, he solved on a 8x8 mesh. Okay, 64 cells. That's all he could do in those computers in those days. All right, but I mean, it was breakthrough work. If you look at, I think I have the reference here. If you look at this paper has more than 5,000 citations. Okay. So Brian Spalding, he's still active. He's almost 100 years old now. I still see him in conferences, and he sits there and literally, if you give a talk in front of him, he's sitting there and taking notes. Okay, he's still that sharp. He, of course, came up with also a commercial flow solver, which is called Phoenix. Some of you may have heard of it. It used to be a pretty popular code in Europe for a long time. And this is, you know, this is before the time we are talking about when Windows existed, okay? I mean, you had only that one screen with green letters, and that's it. Everything had to be done using command prompts on these IBM workstations. Okay, so Phoenix that Spalding developed everything was input file based. You know, you could even generate a little mesh using an input file through some commands and then run your flow solver using that input file. There were no Windows graphical user interfaces, nothing like that. Okay, so it was a pretty popular code for a long time. Now it has kind of faded out, but I think even in Europe, especially in the UK, is still being used to a great extent. Patankar is now a distinguished professor at University of Minnesota. And again, you know, he's also pretty active. I think he also has a company of his own. I see him off and on giving plenary lectures and stuff like that. One of the references that I have in your syllabus, 1980 book, Hemisphere publication by Patankar, it's still considered a gem. Okay, the problem with that book, of course, is it's a 1980 book, so it doesn't talk about complex geometry and unstructured mesh and all that. Everything is for a Cartesian mesh, you know. Nothing is generalized. Everything is written for a simple mesh like that, but it is probably the best book if you want to learn about these pressure-based methods. Okay. So that's a bit of history. Now, since its publication, of course, the simple algorithm has been used in, now it's used in all commercial codes. Fluent, Star CCM, CFDA, CFX, every code uses this method. Okay. Now, of course, there has been a lot of developments to this. There have been developments where, for example, people say, we're not going to use segregated solution anymore. We're going to solve the equations in a coupled way, you know, alternative formulation. But it's not the density-based method still. It's still the pressure-based method and so on. Okay. So simple, when somebody says, okay, what is this? If I asked you, okay, one sentence answer, what is the simple algorithm? You should have it very clearly in your head. It is not the finite volume method. It is not, you know, it is not the pressure-based method itself. Simple refers to the method used to address velocity-pressure coupling. In other words, how do we use the continuity equation to figure out pressure? That's what it refers to specifically. Okay, so have that very clear in your head, that simple algorithm is simply an algorithm to treat pressure-velocity coupling. Okay. So what's the first step? So I'm kind of looking at this like a recipe, but what I have done here is I'm going to go through each step, and in each step, whatever are the missing holes, I'll fill them in, okay, including all the derivations. And then later on, towards the end of next class, I will actually summarize it in the form of a flowchart. okay, where we will just say, okay, this is what you know, just go back to the previous lecture and look at the derivation and the detailed equations, okay? All right, so we start with UVP at the cell centers, all right? And I'm assigning an iteration index K to it because as we know, we have an outer iteration loop that we are going to go through. So this would be basically K equal to 0, okay? So U with the superscript K within parentheses essentially means U at the kth iteration, V at the kth iteration, P at the kth iteration. By iteration, I mean outer iteration, okay? We calculate our link coefficients for both X and Y momentum equations using formula outlined earlier. So that was the previous 8 or 9 slides where I had all the formulas, okay? So you calculate those. In terms of code, this will be 2 major chunks of your code. You will have a function or a subroutine which will say calculate X coefficient links, calculate Y coefficient links and sources, okay? Basically assembly of the matrix. You calculate pressure sources, I just mentioned that, and then in step 2, you're now going to predict a new velocity field, both U and V, by solving the 2 momentum equations. Okay? Remember, link coefficients already had this U, V, etc., but there was the advected velocity component, which we are really solving for, which is basically, if I just go back here, I'm trying to solve this equation. It's a linearized form of the momentum equation, where this already has U, V, but they are using old values, and then I'm predicting a new value, okay? So that's the idea there in step 2, that you're solving the 2 momentum equations, and the new solution, I'm going to call it U hat and V hat, okay? Now I have some notes here, which says the momentum equations are generally solved iteratively. That's where you use inner iterations because our matrix sizes are large. You can't use Gaussian elimination, okay? They are solved in correction form, which is something we talked about in the previous class, okay? And they are solved only to partial convergence. Now here I want to make a note. The reason we solve them in correction form is because you have to apply inertial damping. Otherwise these nonlinear equations will blow up, okay? So that's why you solve it in correction form. And you solve them to partial convergence. Why do you solve it to partial convergence? Because you know that, okay, if I solve U momentum to machine accuracy, it doesn't help anything because ultimately I have to go back and resolve it again, okay? So why solve the X momentum to machine accuracy, okay? It's kind of like, you know, 3 people advancing and the target is all 3 should reach that wall simultaneously. You know, if I'm super fast and I just run to that wall and the other 2 guys are here, it doesn't help anything. I have to come back and then say, hey man, come on, move. Okay. So that's the idea, that solving one equation to machine accuracy doesn't help. You all want to work in unison. Okay, so that's why we solve them to partial convergence. Now, what do we exactly mean by partial convergence? How much convergence? Those are details we'll talk about down the road. Okay? So, this is where it gets really important to understand the concept. So, the velocity field that you predict, U hat and V hat I'm calling it, okay? This satisfies momentum conservation, but not mass conservation, since it still uses the old pressure field, okay? Imagine that we buy into the concept that the pressure is calculated by the continuity equation, okay? But this pressure that I'm using here in my equation, let me just go back here, okay? Either this equation or this equation, okay, these sources, they use P from the previous iteration, right? Because I still haven't solved continuity equation in this current outer iteration. I've solved it in the previous iteration, so these pressure fields are old. Now, if I were to say that I actually conserve mass and momentum both, then I need to, in this equation itself, I need to consider the latest pressure field, which I don't have. I haven't solved for it yet. Okay, so this is still using the old pressure field. So it is almost like, okay, I plug in a number here and then I solve this. This is an approximate solution to the momentum equation. It uses an old, pressure field. It's partially converged. The link coefficients have been linearized out. So there's all these approximations. So whatever I predict out of solution of this equation, I mean, I'm saying, yes, it conserves momentum, but it actually conserves even the linearized momentum equation, not the actual momentum. And definitely it doesn't conserve mass, that solution U hat and V hat that I calculate out of this equation. Okay? Everybody with me so far? So that's what we're saying here, that these guys conserve momentum, but not mass. Okay? Now, so these are the velocities that satisfy these momentum. So what I've done is, instead of using U and V and so on, I'm using U hat and V hat here, because that's the equation they're actually satisfying. Okay? And I've written it in compact form using that neighbor symbol so that they're easy to write. Okay? Notice that this pressure field is still at iteration K, old iteration value, old outer iteration. If I go back to my algorithm here, okay, if I'm solving this for the very first time, the pressure field that I'm using here to solve this is basically my guess pressure at K equal to 0. I'm now within K equal to 1, but the pressure field at K equal to 1 will be calculated here. I don't have that yet. I'm still using K equal to 0. Okay, so at the current iteration, which I'm calling K plus 1, I'm still using pressure from iteration K. Okay, that's the idea that I'm showing here. Now, what I've done here, and now this is where I'm going through the derivation. Okay, so don't think of it as, okay, are these the equations he's going to code in and finally solve? No, I'm going to actually solve these equations iteratively. But I can also write that equation in a different way, where what I've done is I've translated the neighbors onto the right-hand side. Now notice I'm not saying that these are still implicit equations, okay? I'm not saying that the neighbors will be treated using old values or anything. It's just another way of writing the equation. Neighbors and node naught, they're still both implicit, unknowns, okay? It's not like, you would write in a Gauss-Seidel iteration where the neighbors are old values. That's not what I'm doing here. I'm just rewriting this equation in a different way for the purposes of derivation. Okay? Everybody clear on that? All right, so here's my U hat, V hat, just this equation divided through by the diagonal, and then the neighboring terms transposed over to the right-hand side. Okay? Now, if we had used the correct iteration pressure field instead of the old pressure field, that is pk plus 1 instead of pk, then the resulting velocity field would have satisfied both mass and momentum, right? Because then we would have said that, okay, at an iteration k plus 1, I'm solving the momentum equation, but I'm using the pressure that I have here. Okay. Now, realistically, that's not possible, obviously. So, okay. So this is a hypothesis. We're saying that if we somehow had the pressure already by solving the continuity, okay, then if I used it in the momentum equation, what am I saying? I'm saying my pressure field already satisfies continuity. Now, I'm solving a velocity field by plugging it into the momentum equation, which means I'm satisfying both momentum and continuity, both equations. Okay? But unfortunately, I don't have the pressure field here. But I can say that if I had that, then that's what would happen conceptually. Okay? So this is what we're saying here. That if I used pk plus 1 in these equations instead of pk, then ideally I can say I would have satisfied both mass and momentum conservation. Okay? Now let us now assume that the correct or current iteration pressure field is somehow known. This is what I was just saying, that let's pretend it's known. Okay? How? We'll come to that later, but let's say we know. Now if we use that pressure field, the latest pressure field, then we are also, if we solve the momentum equation, we're going to get a different solution. It's not going to be the U hat and V hat that we talked about, which uses the old pressure field. If we use the new pressure field, we'll get a different solution. That different solution, we are going to call it U hat and V hat. Conceptually, U double hat and V double hat, okay? U hat and V hat only satisfies momentum conservation. U double hat and V double hat satisfies both mass and momentum conservation. Okay? That's the idea that we are proposing here, or Patankar proposed. So, therefore, we can write the exact same equations, but instead of U hat and V hat, we are now going to use U double hat and V double hat, and instead of PK, we are going to use PK plus 1. Okay? Exact same equation. We are now using the latest values of pressure, and as a result, we are saying the velocity field predicted would be different. It won't be U hat and V hat. We are going to call it U double hat and V double hat. Okay? Everybody with me so far? Okay. All right. Now, if it did satisfy mass and momentum conservation, then we can safely say that the U double hat is nothing but my velocity in the next iteration, okay, or my current velocity field. See, we started at UK and VK right at the top. Then we solved the momentum equation. We got U hat, V hat, right? Then we solved continuity equation in a sense, because we are saying, okay, we are going to use the current pressure. That gives us U double hat and V double hat. So now in that iteration, we have satisfied both momentum and mass. So therefore we can say at the end, at the bottom of that loop, whatever velocity field I had is the same velocity field I have at the top of the loop in the next iteration, or that is UK plus 1 and VK plus 1. Okay? Because if you look at your algorithm here, this is what we are doing. So right here, after we solve X and Y momentum, we have U hat and V hat. After we solve continuity, we have U double hat and V double hat. Now this U double hat and V double hat is really nothing but, since I'm advancing my iteration index by 1, is what ends up going here. And using these now, I'm going to calculate my link coefficients again. Okay, so that is nothing but UK plus 1 and U VK plus 1. Okay, so that's what I'm saying here. All right, now, can anybody say, why do we need to iterate any further? We're saying, okay, we have satisfied both mass and momentum conservation. Why do we need to go back and redo this? So you always have to realize that your equations are nonlinear. Okay? The link coefficients that you calculated yes, here you have a new velocity field, but these link coefficients are still based on what you guessed here. Okay? Remember, you have a U times U, U times V. Only one of those U's or V's or W's are updated. The other one is still old value. Okay? If this was a linear equation, then you perhaps could work it out in a way that you don't have to iterate anymore. But since this is a nonlinear equation, you have to iterate. There is no getting around that. No matter how fancy your scheme is, even if you do a coupled solution, you still have to iterate. Okay? Unless you do a coupled solution of the nonlinear equations themselves, like, for example, you use a Newton's iteration method for a set of nonlinear equations. Okay? Which people actually often do. The finite element people often do that for the Navier-Stokes equations. All right, but even that would require iteration. I mean, a Newton's method requires iterations. It's just a different kind of iteration, not the kind that we are using here. Okay, but the bottom line is, anytime you have a nonlinear equation, you have to iterate. There's no getting around that. So that's why you have to go back and redo this again, because the first part of your rho U, the first rho U is still old iteration value. The second U is what you updated after you did this procedure. Okay? And then, of course, there are other reasons too. Nathan pointed out one reason. The second reason is that you're solving these equations to partial convergence. You're not solving them completely. okay, within the iteration loop, because you know I have to go back and redo this, okay. So by the very fact that you solve them partially doesn't mean it basically means you don't have a converged solution at this point. You have to go back and do it again. All right. So with that velocity field, then you go back and redo the whole thing again. Okay. Now comes the question. So this is where I'm sort of digressing from the flow of the algorithm and getting into derivation. So the big question is, okay, we talked about hypothetically that if we have this new pressure field, we could use it to correct the velocity. But what is this pressure field? How do we get it? Okay, and this is where the velocity pressure coupling comes in. So what we do is we subtract equation 2 from 3. So equation 2 was for u double hat, and equation 2 was for u single hat, and equation 2 was for u double hat. If you go back a couple of slides, okay? So we subtract one from the other, okay? Now, if you think about it, what is this difference? This difference is telling me that it's the difference between the velocity field when I've satisfied just momentum versus when I've satisfied both mass and momentum, okay? So obviously I'm expecting that once I satisfy mass also, the velocity field is going to change, okay? That change is what we are talking about here. All right. So once we do that, we get this equation, and now I can, I'm introducing a new set of variables or new set of symbols, u prime denoting u double hat minus u hat and so on, and then p prime denoting pk plus 1 minus pk. So p prime denotes the pressure change from the new iteration and old iteration, whereas the velocity primes denote velocity changes from the solution of the momentum equation to the solution of the mass and momentum equations. Okay? So those are their definitions. So if I use those new symbols, then these are what the two equations. That's what I get. Okay? You can clearly see here I have p prime, p prime, p prime, p prime, and so on. So I get these equations. These equations, by the way, are simply known as velocity correction equations. Okay? So in the simple algorithm, when we refer to velocity correction, we are always referring to correcting the velocity after we have conserved mass from the velocity that we already got after solving the momentum. Okay? All right, now you can see here there's a bit of a problem. This is an implicit equation, obviously. Okay, I have u prime naught here, u prime neighbor here, and so on. Okay, and what Patankar said is that in simple, I'm going to neglect these first terms. Okay, so he said I'm going to make this correction equation completely explicit for the simple reason, number one, I want to make it very cheap. And secondly, it may not be necessary, okay? So he threw away those two terms. Now, the rationale for throwing away those two terms is those terms, again, vanish at convergence, because at convergence, the velocity never changes with iteration. So let's say you've already reached convergence, okay? Whether you are at the point where you've solved the momentum equation only and then you solve momentum and mass conservation, your velocity still is not going to change. It has become invariant, okay, at convergence. It has already satisfied mass and momentum conservation. So if you solve the mass conservation equation one more time, that's not going to change it, okay? So that's the argument, that these terms actually vanish at convergence, which basically means, again, just like we have talked about so many times, that this is the advantage of correction equations, throwing away that term doesn't change the final answer. It only changes the path to convergence. Okay, it changes how quickly this algorithm is going to converge, or okay, whether it's going to at all converge or not. Those are things that will definitely be affected by throwing away that term. In fact, later on, you will see probably in the next class when we talk about the simple C algorithm, which is a later version of this algorithm. The C actually stands for consistent. Okay, the simple C algorithm, what Raithby did was he said, well, throwing away that term is not so good. It hampers convergence significantly. I'm going to try to make it better. So he will actually manipulate that term further to not get rid of it completely. Okay, that's where the simple C algorithm comes in. So it all has to do with how, I mean, until this point, if you think about it, the mathematics is exact. There are no assumptions. The moment you throw this term away, then you're saying, okay, I'm introducing a new approximation. An approximation that will affect convergence. Okay? So that's when approximations come in, and then this is where, you know, you often get into the problem that simple may not want to converge for a certain problem. All right? So this is what Patankar and Spalding proposed, that we throw away that term, and therefore, when you do that, things become really, really simple. You can see u double hat minus u hat is your u prime, okay? That's this guy. So therefore, your u double hat is, so what we're saying here is the velocity we get after satisfying mass conservation is equal to the velocity we get that we get by solving the momentum conservation equation plus some correction term. Okay, that's all. It's a very simple, explicit equation. There is no, you know, simultaneous equations to be solved and so forth. Now, of course, the question is, how do we get these guys? The pressure corrections. Okay. Now, notice that I asked this question, okay, that how do we get the correct pressure field? I did all this formulation, which gave me these P primes, the pressure corrections. Pressure correction, by the way, is the difference between the old iteration and the new iteration, okay? But I still have not answered this question. Obviously, I don't know P prime now. Instead of Pk plus 1, I have introduced a new symbol, P prime, but I still don't know P prime. Bottom line, I still haven't answered that question, so I still need to answer that question. And the key to that answer lies in, obviously, the continuity equation, because we have been saying repeatedly that this new pressure field must satisfy continuity equation. Then only we can say the velocity field satisfies continuity. Okay? So that's where the key lies. And so I'm bringing back that question, how do we obtain this pressure field? Okay? Finally, we satisfy the mass conservation or continuity equation. So here is what we do. Okay, now our target control volume is this green control volume. This is where we are satisfying mass conservation. Okay. So if I write down the the finite volume formulation for the continuity equation at steady state, this is what we get. You already know this: rho east u east minus rho west u west times delta y. Plus rho naught v naught minus rho south v south times delta x. Basically, eastern phase times the area minus western phase times the area plus northern phase times the area minus southern phase times the area. Okay, the delta x and delta y in this case represent areas. Very simple equation. Okay, and this is where again, last class I may have confused you a little bit, but this is where I'm saying you cannot use distance-weighted interpolation for the velocities. Okay? If you do that, then your pressure field will never converge. And we'll talk about, before we get into collocated mesh, we'll talk about why that happens. Okay? But that's what we are saying. Now, of course, by staggering the grid, now we have an example, because you can clearly, we have an advantage, because clearly you see on the faces of the green control volumes, I actually have x momentum nodes sitting right there. Okay, so my u east is nothing but that velocity, and my u west is nothing but that velocity, and I am actually calculating the velocities right there. Okay, that is the advantage that we get by staggering the mesh. So therefore, u small east becomes u capital east, and u small west becomes u naught, and so on. Okay, so that's the advantage I'm getting here. Now, with regards to the phase densities, these phase densities that I have here are not the same phase densities that you used in the momentum equation. Again, you have to be careful because you've staggered your grid. Okay, so these densities are simple linear averages because density is stored at the green points. Okay, So rho small east is nothing but, so if I want to calculate the rho here, I'm going to take the average of that and that. Okay. If I want to calculate the density here, I'm going to take the average of that, and so on. Okay. So this is pretty intuitive. There is no, remember for the momentum equation, we got into this scenario where 2 of them didn't require interpolation and 2 of them required 4-point interpolations. Here we don't have that issue. Okay, for the continuity equation. Everybody with me so far? All right. So we already said that the velocity field u hat and v hat satisfy both mass and momentum conservation. Therefore, we are going to now force it. Basically, we are forcing this velocity field to satisfy mass conservation. It already satisfies momentum conservation. Okay. But now we are forcing it to satisfy mass conservation also, because we are plugging it into the mass conservation equation. Okay. Here, we forced it to satisfy momentum. That's what these equations represent. Okay. Now we are saying we are also going to force it to satisfy mass conservation, which is represented by that equation. Okay. And instead of using north, east, west, and so on, I've used IJ notations here because it kind of makes life a little easier down the road. So you see here the eastern I've replaced by I plus 1, the north I've replaced by I, and so on, and similarly northern and north. Okay. So now what I'm going to do is I'm going to take the u double hat and replace it with this velocity correction expression that I just derived a couple of slides ago. So I'm going to take this expression here and replace that by the right-hand side of that equation. Okay? So we are using equation 4 here. Substituting that in. All right? Everybody with me so far? All right. Now we rearrange this in standard 5-band form. So you see there is a P naught prime, P naught east, P naught west, or sorry, P prime west, P prime south, P prime north, and so on. Okay? And now we replace that or rewrite that using this form. So when you do that, you see that, for example, this term will contribute, there will be one contribution to the diagonal and one contribution to the eastern coefficient. This term will have a contribution to the western coefficient, one to the diagonal. One to the diagonal, one to the northern coefficient, one to the southern coefficient, one to the diagonal, and so on. And then these guys here, we're going to transpose it all over to the right-hand side and call it S naught P. Okay? So everything with a single hat, we are going to throw to the right-hand side of the equation and call it S naught P. All right? So that's what this equation is. And once you do that, these are what your link coefficients come out to be. So this is simple algebra, basically comparing it to the 5-band form and then figuring out what those coefficients are. Okay? Now notice that the diagonal in this case adds up to the sum of the off diagonals. Okay? If you go back to the previous iteration, every term that has a naught has a corresponding off diagonal subtracted from it. Okay? Everywhere. Which means that the diagonal will add up to the off diagonal. Okay? Now what does that indicate? That indicates that this pressure correction equation that I just derived is nothing but a discrete form of a Poisson equation. Because that's what you get for a diffusion or Poisson equation. You know that already from what we have discussed before. That a classic symptom of a Poisson equation is if you discretize it, no matter what method, finite volume, finite difference, doesn't matter, the diagonals add up to the off diagonal. Okay, which does not happen for an advection diffusion equation. I also discussed that in the past, that the moment you add the advection term, you have this mass imbalance show up. The diagonal doesn't add up to the off diagonals. Okay, but for a diffusion equation, it does. Okay, so this is actually a Poisson equation for pressure correction, not pressure. Okay? Now, let's talk about the right-hand side. So if I take these terms, this one, that one, that one, that one, and throw them over to the right-hand side, what do I get? I get something that looks like that. Okay? Now notice that this is like your continuity equation. You have eastern phase, eastern flux, western flux, northern flux, southern flux of mass. Okay? So really this is nothing but a mass imbalance with a negative sign in front of it. Okay? Now, what does this mass imbalance represent? This mass imbalance, if you look at this, notice that there is u hat on all these velocities, not double hat. So what this is saying is as follows, that after I solve my momentum conservation equations, okay, I take the velocity field and plug it into my continuity equation, I'm going to get a mass imbalance. In other words, that velocity field, if I calculate in each control volume using that velocity field, every control volume will have a mass imbalance. Okay? That's this mass imbalance that I'm showing here in this equation. You use that as a source term for another equation, your pressure correction equation. Okay? That pressure correction equation is now taking that mass imbalance as a source and saying, oh, I have too much mass in this control volume. Therefore, I need to adjust the pressure such that the fluid is either pushed outward or comes into the control volume. Okay? So the mass imbalance acts as a source to adjust the pressure. Once you adjust the pressure, what happens is that once you adjust the pressure or calculate these guys, your velocity field also gets adjusted. So the new velocity field that you will calculate after you adjust the pressure will now satisfy mass conservation also. Okay? So this is the philosophy we are using. We're solving the momentum equation. That velocity field creates a mass imbalance. That mass imbalance now adjusts the pressure. That adjustment of the pressure now gives me a new velocity field which satisfies both mass and momentum conservation. Okay? So this is what we are really doing here. We are taking this mass imbalance as a source term for our pressure correction equation, which gives me my new pressure. Okay, so a little bit more discussion, physics of this term. So I already talked about this. So if you look at this pictorially, this is what's going on. Okay, the quantity within this square brackets, this quantity here, represents net mass out of the cell. Why? Because we are taking eastern, which is that guy, minus western, which is that guy. Okay, and then we are taking northern, which is this guy, minus southern, which is that guy. Okay, so this is net mass out of the cell. So since I have a minus sign in front, that S naught P, this guy here, my source term, is nothing but net mass into the cell. Okay? So what we're saying is my pressure correction equation is as follows. I have A naught P naught prime plus the sum of the neighbors is equal to net mass imbalance into the control volume. Okay? Now think about it physically. Imagine a situation where you have too much mass coming in and not as much leaving. So you have calculated a velocity field that from your momentum equation, which makes too much mass come into a control volume and not as much leaving. Okay? So now we are asking, okay, if that happens, what's going to really happen to the pressure in that cell, in that control volume? All right? So you can clearly see here, if this is positive, if net mass comes in, then your P naught that you predict is going to be positive. Why? Because your diagonal is also positive. If you look at this guy here, this is all positive. Okay? So, sorry. So that's what we're saying here, that this will result in the pressure correction in the cell to be positive because this is positive, the diagonal is positive, okay? And let's say for the sake of argument, just to understand this, that these are very negligible, okay? What that means is that you are going to get a positive pressure correction. Positive pressure correction means you had a previous iteration pressure, now the pressure is going to go up, okay? If the pressure in that cell goes up, it's going to force fluid out of that cell in the next iteration. And so you had too much mass in the cell, now that is going to get corrected in the next iteration. More mass will leave that cell. It will force mass to leave that cell, and the pressure will come down then the following iteration. Okay, so this is an equilibrating mechanism in a sense. The pressure is constantly adjusting itself in such a way that mass and momentum are both conserved. Okay. Here's a question for you. This is a problem that you guys will solve, and I'm pretty sure everybody knows about this. Okay, I ask my students this question quite often because it's helpful for understanding. So suppose I have a simple channel flow. Okay, could be a pipe, could be a two-dimensional duct, it doesn't matter. Okay, and let's say at the inlet here I have a plug velocity profile. Okay, now right here, once the flow becomes fully developed, you all know from your fluid mechanics you're going to get this nice parabolic profile, right? Everybody knows this? Anyone who doesn't know this? Okay, does anybody remember what the centerline velocity is compared to, so if this velocity was u in, what's the centerline velocity? So for a pipe, it's 2 times u in. So this is what it came in with. It's grown to twice that size at the center line. What caused it? What's the fundamental mechanism that caused it? No, pressure, the pressure difference you get is because you have friction at the walls. Conservation of mass. That is very, very important to understand. Okay? So, suppose I take this problem, and this is something, you know, I talk about with my students all the time when they solve their Navier-Stokes equation, let's say for a channel flow. So here's the thing. I'll draw an analogy so you can understand. Suppose instead of u in, now I think about a passive scalar, phi in. Okay? And let's say the value of phi is equal to 0 here, phi is equal to 0 here, just like you have u equal to 0 here and u equal to 0 here. I'm drawing an analogy. If I solve this problem and flow, let's say, is in that direction, okay? And let's say phi in is equal to 1. For the sake of argument, we make up some number. So 1 at the inlet, 0 at the walls. Okay? You can think of phi as temperature, non-dimensional temperature or concentration, something like that, to ease your understanding. Once you solve the governing equation for phi, will ever phi exceed the bounds of 0 to 1? If you don't have a source term? If I have, for example, temperature, if this is 400 Kelvin and this is 300 Kelvin walls, can the temperature go above 400 Kelvin? It can't, right? Same thing for concentration. If this is red dye coming in and this is blue dye, there is no way that it will become super red. In other words, phi becomes 2. Impossible. Okay? But look at what's happening to velocity. You're exceeding the inlet velocity at the center line. So right away you have to think there is something else going on here. If I just solved the momentum equation, there is no way I'm going to get 2u in. I'm going to get a velocity. And I tell my students always, when you're debugging your code, after you solve your momentum equation, look at your velocity field. You should see all velocities less than the inlet velocity. If you don't, then your momentum solver is wrong. Okay? Don't come and tell me my momentum solver is giving me 1.1 times the inlet velocity. That's wrong. You may think it's right because you're expecting it to go to 2, but it's wrong. Only after you enforce mass conservation, this can happen. Okay, momentum conservation alone will not give you that. So now what's happening really is that you solve your momentum equation. Let's say here you get a velocity profile, the peak of which is about 0.7 u in. Okay? You feed that into now your mass conservation equation. Your mass conservation will tell you, wait a minute, you have, velocity of 1 here. Here you have an average value of 0.8. That's imbalance. Something has to happen. Okay. Now, of course, in a 1D sense, it doesn't work. But the bottom line is this. The velocity is slowing down here due to friction. Okay. So less mass is flowing here on the outer peripheries compared to what came in. So therefore, more mass has to flow through the center line. Okay. So the fluid actually, if you look at the V velocity components in a channel flow, in the entry region, they're pointing inwards towards the center line. If you plot the vectors, okay, you will get these little vectors like that. Strong, in these corners, you'll get strong V velocities pointing inwards. That's pushing the mass constantly towards the center line. Because by mass conservation, it realizes that, well, I'm slowing down here, something else has to compensate for that. That's why it bulges to 2 times the inlet velocity. Okay, so that the average mass flux here is exactly equal to the average mass flux there. If I sum over the entire cross-sectional area. But if you just solve the momentum equation, you'll never get that. Okay? Everybody clear on that? So it is 2 mechanisms simultaneously at play when we're talking about fluid mechanics. All right, it's not, you cannot interpret its results simply by conservation of the momentum equation. All right, so let's move on now. So after we have solved the velocity, the pressure correction equation, so I already outlined for you what to do here. So, let me just go back here. So these are your link coefficients. This is your source term, and you just solve it now. Okay, and the solution again is iterative inner iterations. Okay, the only difference is this is now a diffusion type equation rather than the advection in diffusion equation which you had for momentum. Okay, but the idea is the same. So once you solve the pressure correction, then all you have to do is you have to correct everything. Okay, so you say, okay, my new pressure is my old pressure plus the pressure correction, and my new velocity is the old velocity plus the velocity correction, and the velocity correction has already been expressed in terms of pressure correction. Okay, so this here is the velocity field that I got by solving the momentum equation. Now I'm correcting it because this new pressure field satisfies the continuity equation also. Okay, now the pressure corrections that we often compute using simple is over-predicted. Okay, this is a common thing that people have observed. Now, I think in your notes I say slide 21, but that's because, I had an old set of slides, slide 8. So I'm talking about, we go back a couple of slides, right here. Remember, we threw out these terms. Okay? Now notice that there's a negative sign here in front. So you think about this. Since I threw away this negative term here, generally what happens is the pressure correction, the velocity correction that you predict out of this expression, it's over-predicted. Okay, so you have to damp it out. So one of the things that is almost mandatory and necessary for the simple algorithm is the use of so-called linear relaxation factors. So what you do is, instead of using this or that, you apply a damping factor there. So what you're saying is, my new velocity that I'm calculating after I conserve mass is going to be the velocity field that I got by conserving momentum plus only a fraction of the correction that I predict. So if let's say my velocity after solving the momentum was 0.5 and I predicted a correction of 0.2, I'm saying I'm not going to take 0.2, I'll take a small fraction of it, okay, maybe half of it. So it's going in the right direction, but I don't let it go completely because I've made a mathematical approximation in deriving this. If this was exact mathematics, I wouldn't have to worry about it, okay? But since this is inexact mathematics with approximations built into it, I often have to use these linear damping factors, okay? So both velocities get linear damping factors and so does the pressure because again, the same thing, you over-predict the pressure correction. So you're damping out the pressure as well as the velocities before you go to the next iteration, okay? Now I'll talk about what typical values you use for these damping factors, but we'll reserve that for later. Okay. For now, just understand that these are damping factors between 0 and 1. Okay. And they're typically known as under relaxation factors.